In 1789, an astronomer named William Herschel pointed his telescope towards Saturn and noticed something no human had ever seen before: a tiny speck of light orbiting the ringed giant. He had just discovered a moon, one that would later bear his name in a very unexpected way. But Herschel could never have imagined what this small, icy world truly looked like. It would take nearly 200 years and a spacecraft traveling over 1 billion kilometers before humanity would finally see the face of this moon. And when we did, the resemblance was so striking, so impossibly perfect, that it sent shockwaves through both the scientific community and popular culture. This is Mimas, the smallest known astronomical body that is rounded due to its own gravity, and it looks exactly like the Death Star from Star Wars. Let's start at the beginning with that moment of discovery. William Herschel was no ordinary astronomer. He was a musician by trade, a German-born composer and oboist who had moved to England and become fascinated with the night sky. He built his own telescopes, grinding mirrors by hand with a precision that rivaled professional instrument makers. On September 17, 1789, using his massive 40-foot telescope, the largest in the world at the time, he spotted Mimas. It was the sixth moon of Saturn to be discovered, and at the time, it was little more than a point of light. Herschel could determine its orbit, estimate its distance from Saturn, and calculate how long it took to complete one revolution around the planet. But he could not see any surface features. He could not know that this moon harbored a secret that would connect it to a fictional superweapon nearly 2 centuries later. For almost 200 years, Mimas remained a mystery. Astronomers knew it was there. They could track its orbit. They could estimate its size, roughly 400 kilometers in diameter, making it one of the smaller moons in the solar system. But its surface was invisible to Earth-based telescopes. Even the most powerful observatories could only see it as a fuzzy dot. Scientists speculated about what it might look like. Was it smooth like Europa? Heavily cratered like our own moon? Did it have any unusual features? Nobody knew. Then came the space age, and everything changed. In 1980, NASA's Voyager 1 spacecraft flew past Saturn on its grand tour of the outer solar system. As it approached the ringed planet, it turned its cameras toward Mimas, and for the first time, humanity saw the surface of this distant moon in detail. The images that came back were nothing short of astonishing. There, dominating almost 1/3 of the moon's visible surface, was a colossal impact crater. It was enormous, far larger than anything scientists had expected. The crater measured approximately 130 kilometers across, nearly 1/3 of the moon's entire diameter. To put this in perspective, if Earth had a crater with the same proportions, it would be about 4,000 kilometers wide, roughly the distance from New York to Los Angeles. The impact that created this crater must have been catastrophic, coming within a hair's breadth of shattering Mimas into pieces. But it wasn't just the size of the crater that caught everyone's attention. It was its appearance. The crater has a massive central peak, rising about 6 kilometers from the crater floor. Combined with the crater walls and the overall shape, the resemblance to the Death Star from Star Wars was unmistakable. The fictional space station, designed to destroy entire planets, had a large circular dish that served as the focusing point for its superlaser. Mimas, with its giant crater and central peak, looked almost identical. The coincidence was so remarkable that it became one of the most famous images in planetary science. Here was a real moon orbiting Saturn that looked like something straight out of science fiction. The timing of this discovery adds another layer of intrigue to the story. Star Wars was released in 1977, 3 years before Voyager 1 reached Saturn. The designers of the Death Star had no idea that a moon matching their creation actually existed in our solar system. It was pure coincidence, a cosmic joke of sorts. The universe, it seemed, had beaten Hollywood to the punch by about 4 billion years. The crater was named Herschel, in honor of the astronomer who first discovered Mimas. And Herschel crater, as it is officially known, has become one of the most studied features in the outer solar system. Scientists have spent decades analyzing the data from Voyager and later from the Cassini spacecraft, trying to understand how this crater formed and what it tells us about the history of Mimas and the Saturn system as a whole. Let's talk about the impact itself. To create a crater this large on a body this small, you need an object of significant size traveling at tremendous speed. Scientists estimate that the impactor was probably around 5 to 10 kilometers in diameter, roughly the size of the asteroid that killed the dinosaurs on Earth. But while Earth absorbed that impact and survived relatively intact, Mimas is much smaller and much less massive. The impact that created Herschel crater nearly destroyed the moon entirely. In fact, calculations suggest that if the impactor had been just slightly larger or had been traveling just slightly faster, Mimas would have been shattered into fragments. Instead of a moon, we might have another ring around Saturn made up of the debris from a destroyed world. The fact that Mimas survived at all is remarkable. The energy released by the impact would have sent shock waves through the entire body. On the opposite side of the moon from Herschel crater, there are patterns of fractures and grooves that scientists believe were caused by these shock waves focusing on the far side. The impact didn't just create a crater, it nearly tore Mimas apart from within. Herschel crater has some impressive statistics. Its diameter of 130 kilometers means it covers about 1/3 of Mimas's face when viewed from certain angles. The crater walls rise approximately 5 kilometers above the surrounding terrain, and the floor of the crater sinks about 10 kilometers below the rim. That central peak, the feature that makes the Death Star comparison so apt, rises about 6 kilometers from the crater floor, almost reaching the height of the surrounding walls. For comparison, Mount Everest is about 9 kilometers above sea level. The central peak of Herschel crater would be a substantial mountain on Earth. Central peaks in impact craters form through a process that seems almost counterintuitive. When an asteroid or comet slams into a planetary body at high speed, it creates a shock wave that compresses the surface material and then rebounds. Think of it like dropping a stone into water. There's a splash, and then the water in the center rebounds upward before settling down. In a large impact crater, the same thing happens with rock and ice. The material at the center of the impact zone rebounds upward, creating a peak. In smaller craters, this rebound isn't strong enough to create a noticeable peak, but in large craters like Herschel, the central peak can be enormous. Mimas itself is a fascinating world beyond just its famous crater. It is the innermost of Saturn's major moons, orbiting at a distance of about 186,000 kilometers from the planet center. This puts it just outside Saturn's main ring system. And in fact, Mimas plays an important role in shaping those rings. Its gravitational influence creates what astronomers call the Cassini division, a dark gap in Saturn's rings that is visible even through small telescopes from Earth. Particles in the rings that would orbit in the Cassini division are in orbital resonance with Mimas. For every orbit they would complete, Mimas completes exactly 2. This resonance destabilizes their orbits, sweeping the gap clean of material over time. The Moon completes one orbit around Saturn in approximately 22.5 hours. It is tidally locked to Saturn, meaning the same face always points toward the planet, just as our Moon always shows the same face to Earth. This tidal locking happened long ago, as Saturn's gravity gradually slowed Mimas's rotation until it matched its orbital period. As a result, there is a near side of Mimas that always faces Saturn and a far side that always faces away. Herschel crater is located on the leading hemisphere, the side that faces forward as Mimas moves through its orbit. This is significant because leading hemispheres tend to accumulate more impact craters as they sweep up debris like a car windshield collecting bugs. Mimas is composed primarily of water ice, with a small amount of rock mixed in. Its density is only about 1.15 grams per cubic centimeter, just slightly denser than pure water ice. This tells scientists that Mimas is mostly ice with perhaps a small rocky core. The surface temperature is brutally cold, around minus 200 degrees Celsius. At these temperatures, water ice behaves almost like rock, maintaining its shape and structure over geological timescales. Despite being so small and so cold, Mimas has some intriguing mysteries that scientists are still working to understand. One of the most puzzling is related to the distribution of heat on its surface. When the Cassini spacecraft mapped the thermal emissions from Mimas, scientists expected to find a fairly uniform temperature distribution, with the warmest areas being those that receive the most sunlight. What they found instead was bizarre. There was a sharp V-shaped boundary in the thermal data, with one region significantly warmer than expected and another significantly cooler. The pattern didn't match what sunlight alone would produce. Even stranger, the warmest region corresponded roughly to the area around Herschel crater, but the pattern couldn't be explained by the crater alone. Scientists have proposed various explanations for this thermal anomaly. One possibility is that the surface composition varies across Mimas, with some regions being better at absorbing and retaining heat than others. Another possibility involves the way Mimas's surface interacts with charged particles from Saturn's magnetosphere. The leading hemisphere, which includes Herschel crater, is bombarded by electrons that flow along magnetic field lines. These electrons might alter the surface properties in ways that affect how it absorbs and emits heat. The mystery remains unsolved, adding another layer of intrigue to this already fascinating moon. Another puzzle involves Mimas's interior. For a long time, scientists assumed that Mimas was a relatively simple body, a frozen ball of ice and rock with no internal activity. But recent data suggests this might not be the case. Careful measurements of Mimas's orbit and rotation reveal subtle wobbles that are larger than expected. These wobbles, called librations, can tell scientists about the internal structure of a planetary body. The librations of Mimas are so pronounced that they suggest one of two possibilities. Either Mimas has an elongated, rugby ball-shaped core, or it has a subsurface ocean of liquid water. The ocean hypothesis is particularly exciting. If Mimas has a liquid water ocean beneath its icy surface, it would join a select group of worlds in the outer solar system that might harbor habitable environments. Europa, Enceladus, Titan, and possibly Ganymede are all thought to have subsurface oceans. These oceans are kept liquid by tidal heating, the gravitational flexing caused by their host planets. But Mimas seems like an unlikely candidate for an ocean. It is smaller and less geologically active than Enceladus, which famously has geysers of water vapor erupting from its south pole. Mimas shows no such activity. Its surface is ancient and heavily cratered, with no signs of recent geological processes. And yet, the wobbles are there, demanding an explanation. If Mimas does have an ocean, it would force scientists to reconsider their assumptions about where liquid water can exist in the solar system. It would mean that even small, seemingly dead moons might harbor hidden reservoirs of water. The implications for the search for life would be profound. Some scientists favor the elongated core explanation. In this scenario, Mimas formed with a core that is not perfectly spherical, but instead stretched along one axis. This could have happened during the moon's formation, as material accumulated unevenly. An elongated core would produce the observed librations without requiring a liquid ocean. But this explanation has its own challenges. It's not clear how such a core would have formed or why it would have maintained its shape over billions of years. The debate continues, and resolving it will require more data. Unfortunately, no spacecraft is currently planned to visit Mimas specifically. The Cassini mission, which provided most of our detailed knowledge of this moon, ended in 2017 when a spacecraft was deliberately crashed into Saturn's atmosphere. Future missions to the Saturn system are in various stages of planning, but they tend to focus on more obviously interesting targets like Titan and Enceladus. Mimas, for all its Death Star charm, is not at the top of the priority list. Let's return to Herschel crater and explore it in more detail. The crater is so large relative to Mimas that it distorts the moon's overall shape. Mimas is not perfectly spherical. It is slightly flattened at the poles and bulges at the equator, as you would expect for a rotating body. But it also has a noticeable bulge on the side, where Herschel crater is located. The impact that created the crater excavated an enormous amount of material and redistributed it around the moon, affecting Mimas's mass distribution and shape. The crater walls are terraced, meaning they step down from the rim to the floor in a series of ledges. This terracing is common in large impact craters and is caused by the walls collapsing inward after the initial excavation. When the impact first occurs, it creates a deep, bowl-shaped cavity. But the walls of this cavity are unstable, especially in the low gravity of a small moon like Mimas. They slump and slide, creating the terraced appearance. The floor of Herschel crater is relatively flat, which is also typical of large craters. In smaller craters, the floor often retains the bowl shape created by the impact. But in larger craters, the floor rebounds after the impact and then collapses back down, creating a flatter surface. The central peak rises from this flat floor, a frozen monument to the violence of the impact that created it. Scientists have used the size and shape of Herschel crater to estimate when it formed. Crater counting is one of the primary tools for determining the ages of surfaces in the solar system. Older surfaces have more craters because they have been exposed to impacts for longer. By counting the number of small craters inside Herschel crater and comparing this to the number on the surrounding terrain, scientists can estimate how long ago the big impact occurred. The results suggest that Herschel crater is very old, probably forming during the late heavy bombardment, a period about 4 billion years ago when the inner and outer solar system were subjected to an intense barrage of impacts. This was the same era that created most of the large craters on Earth's moon and the other terrestrial planets. The impactor that created Herschel crater probably came from the outer solar system, perhaps from the Kuiper Belt or even the Oort cloud. These distant reservoirs of icy bodies occasionally send comets and asteroids into the inner solar system, where they can collide with planets and moons. The Saturn system, with its massive gravity well, would have attracted many of these wandering objects. Some would have hit Saturn itself, disappearing into the gas giant's atmosphere. Others would have struck the rings, adding to their mass or creating temporary disturbances. And some, like the object that created Herschel crater, would have collided with moons. It's worth considering what the impact would have looked like if anyone had been there to witness it. The impactor, traveling at perhaps 20 kilometers per second, would have appeared in the sky as a growing point of light. In the final seconds before impact, it would have been visible as a distinct object, perhaps a few kilometers across, hurtling toward the surface. Then, in an instant, everything would have changed. The impactor would have struck the icy surface with the force of billions of nuclear weapons. A blinding flash of light would have illuminated the entire moon. A plume of debris would have shot upward, some of it reaching escape velocity and flying off into space, while the rest rained back down on the surface. Shock waves would have rippled through Mimas, fracturing the ice and rock deep below the surface. The ground would have heaved and buckled, and when the chaos finally subsided, Herschel crater would have remained, a permanent scar on the face of this small moon. The comparison to the Death Star is not just a fun pop culture reference. It actually tells us something about the relationship between science fiction and real science. When George Lucas and his team designed the Death Star for the original Star Wars film, they were creating a weapon of unimaginable power, capable of destroying entire planets. The design, a spherical station with a large circular dish, was meant to convey technological menace. They had no idea that nature had already created something similar billions of years ago, orbiting Saturn. This kind of coincidence happens more often than you might think. Science fiction writers and filmmakers often draw inspiration from real science, extrapolating current knowledge into imagined futures. But sometimes, the universe beats them to it. The discovery of Mimas' resemblance to the Death Star is a reminder that reality can be just as strange and wonderful as fiction. The cosmos is full of surprises, waiting to be discovered. Since the Voyager flyby in 1980, our understanding of Mimas has grown enormously. The Cassini mission, which arrived at Saturn in 2004 and operated until 2017, made multiple close passes of Mimas, returning thousands of images and vast amounts of scientific data. These observations revealed details that Voyager could only hint at. Cassini showed us that Mimas' surface is heavily cratered, as expected for an ancient, geologically inactive world. Besides Herschel, there are numerous other craters of various sizes scattered across the surface. Many of these craters have their own central peaks, though none as dramatic as Herschel's. The surface also shows linear grooves and chains of small craters, which may be related to the fracturing caused by the Herschel impact or could have formed through other processes. One interesting feature revealed by Cassini is the color variation across Mimas' surface. While the moon appears gray in most images, careful analysis of color data shows subtle differences. Some regions have a slightly bluish tint, while others are more yellowish. These color variations probably reflect differences in surface composition, perhaps variations in the size of ice grains or the presence of different impurities. The leading hemisphere, which faces into the direction of Mimas' orbital motion, tends to be slightly different in color than the trailing hemisphere. This is likely due to the accumulation of different types of particles. The leading hemisphere sweeps up material from Saturn's E ring, which is composed of tiny ice grains ejected from Enceladus's geysers. Speaking of Enceladus, it's worth comparing these two moons. They are neighbors in the Saturn system, with Enceladus orbiting just outside Mimas. They are similar in size. Enceladus is about 500 kilometers in diameter, compared to Mimas's 400. But in terms of geological activity, they could not be more different. Enceladus is one of the most geologically active bodies in the solar system, with a subsurface ocean, hydrothermal vents, and dramatic geysers at its south pole. Mimas, by contrast, appears to be geologically dead, its surface unchanged for billions of years except for the occasional impact. Why this difference? Part of the answer lies in orbital dynamics. Enceladus is in orbital resonance with another moon, Dione, and this resonance creates tidal forces that heat Enceladus's interior. This tidal heating is what keeps Enceladus's ocean liquid and powers its geological activity. Mimas, while it does experience some tidal heating from its proximity to Saturn, does not have the same kind of resonance relationship. Its interior has cooled over billions of years, and any ocean that might have existed is probably frozen solid, unless, as those intriguing libration measurements suggest, something else is going on. The mystery of Mimas's interior is one of the most compelling questions in planetary science today. If Mimas does have a subsurface ocean, it would challenge our understanding of where liquid water can exist. Mimas is smaller than Enceladus and farther from Saturn. It shows no signs of geological activity, no geysers, no young terrain, no evidence of recent ice movement. And yet, the wobbles are there, suggesting something unexpected beneath the surface. Some scientists have proposed that Mimas's ocean, if it exists, might be very young in geological terms. Perhaps it formed recently, within the last few tens of millions of years, due to some change in Mimas's orbit that increased tidal heating. If this is true, the ocean might still be in the process of forming, which would explain why there are no visible signs of it at the surface. The ice shell might not have had time to crack and release any material. This is a speculative idea, but it shows how scientists are trying to reconcile the conflicting evidence. Another possibility is that the librations are being misinterpreted. Perhaps there is some other explanation for the wobbles that doesn't require an ocean or an elongated core. More data would help resolve the question, but as mentioned, no dedicated missions to Mimas are currently planned. Let's step back and consider Mimas in the broader context of the Saturn system. Saturn has at least 146 known moons, ranging from tiny moonlets just a few kilometers across to giant Titan, which is larger than the planet Mercury. Mimas is one of the 7 major moons, along with Titan, Rhea, Iapetus, Dione, Tethys, and Enceladus, that together account for most of the mass in Saturn's satellite system. Each of these moons has its own character and its own mysteries. Titan has a thick atmosphere and lakes of liquid methane. Enceladus has its geysers and ocean. Iapetus has a bizarre two-tone coloration, with one hemisphere dark as coal and the other bright as snow. Rhea and Dione are heavily cratered worlds that may also harbor subsurface oceans. Tethys has a massive canyon system and another large impact crater, Odysseus, that rivals Herschel in size. Among this diverse family, Mimas stands out for its Death Star appearance, but also for its position at the edge of Saturn's main ring system. As the innermost major moon, Mimas interacts closely with the rings, shaping them through gravitational influence. Understanding Mimas is key to understanding the ring system as a whole. The rings of Saturn are one of the most beautiful and iconic features in the solar system. They are made of countless particles of ice and rock, ranging in size from tiny grains to house-sized boulders. The particles orbit Saturn like billions of tiny moons, each following its own path around the planet. But these paths are not random. They are organized into distinct rings and gaps, shaped by the gravity of Saturn and its moons. Mimas is responsible for the Cassini division, the most prominent gap in the rings. This gap, about 4,800 kilometers wide, separates the bright B ring from the dimmer A ring. Any particle that would orbit in the Cassini division is in a 2-to-1 orbital resonance with Mimas. This means that for every one orbit the particle would complete, Mimas completes two. This resonance creates a gravitational tug that pulls particles out of the gap over time. The Cassini division is not completely empty. There are some faint ringlets within it, but it is much less dense than the surrounding rings. Other moons also shape the rings through similar resonances. The intricate structure of Saturn's rings is like a gravitational symphony, with each moon playing its part. Mimas, as the conductor of the Cassini division, plays a leading role in this symphony. The interaction between Mimas and the rings also raises questions about the age and origin of the ring system. For a long time, scientists assumed that Saturn's rings were primordial, forming along with the planet billions of years ago. But recent studies suggest the rings might be much younger, perhaps only 100 to 200 million years old. If this is true, the rings might have formed from the destruction of a moon, either a collision between two moons or the tidal breakup of a single moon that ventured too close to Saturn. Could Mimas have played a role in this destruction? Probably not directly, since Mimas still exists. But the same processes that shaped Mimas, giant impacts, orbital resonances, tidal forces, would have been at work on any other moons in the system. The history of Saturn's moons and rings is intertwined, a complex story that scientists are still piecing together. Now let's consider what it would be like to visit Mimas. Imagine a future spacecraft, perhaps carrying human explorers, approaching this small moon. As you draw closer, the Death Star resemblance becomes unmistakable. Herschel crater dominates the view, its central peak casting a long shadow across the crater floor. The gray, icy surface is pockmarked with countless smaller craters, each one a record of some ancient impact. Landing on Mimas would be a gentle experience. The moon's gravity is only about 1% of Earth's. If you weigh 100 kilograms on Earth, you would weigh just over 1 kilogram on Mimas. You could jump tens of meters into the air with a single bound. A thrown baseball would sail for kilometers before landing. Everything would feel slow and dreamlike. The surface itself would be hard and cold, like frozen concrete. The temperature, around minus 200 degrees Celsius, would require heavily insulated suits and equipment. The sun, over 1 billion kilometers away, would appear as a bright point of light, providing little warmth. Saturn would dominate the sky on the near side of Mimas, a huge crescent of yellow and brown bands, with the rings stretching out on either side. From the far side of Mimas, you would see only stars and the occasional moon crossing the sky. Standing on the rim of Herschel crater would be a humbling experience. The crater walls would drop away below you, a cliff 5 kilometers high. The central peak would rise in the distance, a mountain that took seconds to form but has stood for billions of years. You would be looking at the scar from an impact that nearly destroyed this world, a reminder of the violent forces that shaped the solar system. Exploring the rest of Mimas would reveal a world frozen in time. The surface has changed little since the late heavy bombardment billions of years ago. Craters overlap craters, each one telling a story of some past collision. The linear grooves might mark the paths of ancient fractures, created by the stress of that enormous impact or by tidal forces from Saturn. There might be subtle variations in the ice, different textures, different colors that hint at the moon's history. If Mimas does have a subsurface ocean, you would see no evidence of it on the surface. The ice shell would be tens of kilometers thick, hiding whatever liquid might lie beneath. Detecting the ocean would require instruments that could probe the interior. Seismometers to listen for waves traveling through the moon, radar to map the boundary between ice and water, or magnetometers to detect the telltale signature of a conducting fluid. Such an ocean, if it exists, would be a dark and cold place, very different from the oceans of Earth. But it might still harbor chemistry, perhaps even the building blocks of life. This brings us to one of the most profound questions in science. Are we alone in the universe? The search for life beyond Earth has focused increasingly on the moons of the outer planets, where subsurface oceans might provide habitable environments. Europa and Enceladus are the prime candidates. But if Mimas also has an ocean, it would expand the list of potential habitats. Life, as we know it, requires liquid water, energy, and the right chemical ingredients. Subsurface oceans provide the water. Tidal heating and hydrothermal vents provide energy. And the chemical ingredients, carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur, are common throughout the solar system. The conditions for life might exist in many places beyond Earth, waiting to be discovered. Of course, the existence of habitable conditions does not guarantee the existence of life. Life on Earth arose through a complex series of chemical reactions that we still do not fully understand. It might be that life is common in the universe, arising wherever conditions allow. Or it might be that life is rare, the result of some improbable event that has happened only once. We won't know until we look. Future missions to the outer solar system will help answer these questions. NASA's Europa Clipper mission, launching soon, will study Europa in detail, searching for signs of habitability. The European Space Agency's JUICE mission is heading to Jupiter to study Ganymede and other moons. And there are proposals for missions to Enceladus that would sample the material erupting from its geysers. Mimas is not currently a priority target, but as our understanding grows, that might change. Let's return to the Death Star comparison one more time, because it illustrates something important about how we relate to the universe. When people see the images of Mimas, they immediately recognize the resemblance to the fictional space station. This recognition is powerful. It creates an emotional connection to a distant world that might otherwise seem abstract and remote. Science fiction has always played this role, serving as a bridge between the known and the unknown. Stories about space travel, alien worlds, and cosmic adventures spark the imagination and inspire people to learn more about the real universe. The fact that a real moon looks like a fictional weapon of mass destruction is delightful, a gift from the cosmos that makes astronomy more accessible and engaging. But there's also a deeper point here. The Death Star is a human creation, born from our imagination. Mimas is a natural object shaped by physical processes over billions of years. The resemblance between them is pure coincidence. There is no designer, no intention behind it. And yet, we can't help but see a pattern, a connection. This is how human minds work. We look for patterns, we make associations, we find meaning. It's what makes us curious, what drives us to explore. When we see Mimas and think of the Death Star, we're doing what humans have always done, making sense of the universe through the lens of our own experience. The exploration of Mimas and the Saturn system more broadly is part of a larger human endeavor to understand our place in the cosmos. We send spacecraft to distant worlds not just for scientific data, but because we are driven to explore, to discover, to know. Every image from Cassini, every measurement from Voyager represents countless hours of human effort and ingenuity. The scientists, engineers, and administrators who made these missions possible are part of a tradition stretching back to William Herschel and beyond. A tradition of looking up at the sky and wondering what's out there. Mimas, with its giant crater and icy surface, is one small piece of this vast puzzle. It's a moon that was nearly destroyed by an ancient impact that shapes the rings of Saturn through its gravity, that might harbor a hidden ocean beneath its frozen shell. It's a world that looks like something from a movie, but is far more interesting than any fictional creation. As we continue to explore the solar system and beyond, we will undoubtedly find more surprises, more coincidences, more wonders. The universe is far stranger and more beautiful than we can imagine. And every discovery, whether it's a moon that looks like the Death Star or a hint of water where none was expected, brings us closer to understanding this incredible cosmos we call home. The story of Mimas is far from over. Future observations, whether from ground-based telescopes, space-based observatories, or new missions to Saturn, will reveal more about this enigmatic moon. The question of whether it has a subsurface ocean remains open, waiting for more data. The details of its formation and evolution are still being worked out, and the cultural impact of its Death Star appearance continues to resonate, inspiring new generations of scientists and space enthusiasts. For now, Mimas hangs in the darkness of the outer solar system, orbiting Saturn once every 22 hours, its cratered face turned toward the cosmos. It has been there for billions of years, long before humans existed, long before life arose on Earth. It will be there long after we are gone, a silent witness to the passing ages. And somewhere in the ice, perhaps, there is water, liquid water, the essence of life, waiting to be discovered. And this is perhaps the most profound lesson Mimas has to offer. Here is a moon that was almost shattered into oblivion, that survived against all odds, that carries the scar of its near destruction as a permanent feature. In a way, Mimas is a testament to resilience. The universe is a violent place, full of collisions and catastrophes, and yet worlds survive. They endure. They continue their silent orbits, carrying their histories written in craters and fractures. When William Herschel first spotted that tiny point of light in 1789, he could not have known what he had found. He could not have imagined the giant crater, the Death Star resemblance, the possibility of a hidden ocean. He saw only a new moon, another wanderer in the darkness around Saturn. But that single observation set in motion a chain of discovery that continues to this day. From a point of light to a world with geography, history, and mysteries. That is the power of human curiosity. We live in an extraordinary time. For the first time in history, we can send machines to other worlds and see their surfaces in detail. We can analyze their compositions, measure their temperatures, map their magnetic fields. We are no longer limited to what our eyes can see from Earth. The universe has opened up before us, revealing wonders that previous generations could only dream of. Mimas is just one of those wonders. A small moon, easily overlooked among the giants of the outer solar system. And yet it holds secrets that could reshape our understanding of where life might exist. It bears a crater that connects it to popular culture in an unexpected way. It plays a crucial role in shaping one of the most beautiful structures in the solar system. In its own quiet way, Mimas matters. The next time you look up at the night sky, remember that Saturn is out there with its magnificent rings and its family of moons. And among those moons is Mimas, the Death Star of the solar system, a frozen world with a violent past and an uncertain future. It has been orbiting Saturn for 4.5 billion years through the formation of Earth, the rise and fall of the dinosaurs, the emergence of humanity, and the dawn of the space age. It will continue orbiting long after our spacecraft have fallen silent and our civilizations have turned to dust. But for now, in this brief moment of cosmic time, we have the privilege of knowing it exists. We have seen its face. We have named its crater. We have wondered about its secrets. And in doing so, we have connected ourselves to something far larger than our daily lives, to the grand sweep of cosmic history, to the forces that shape worlds, to the endless mystery of existence itself. That is the gift of exploration. That is why we look up. That is why we send our machines into the void. Not just for data, not just for science, but for meaning, for connection, for the simple, profound joy of discovery. Mimas awaits. The universe awaits. And somewhere out there, among the ice and rock and starlight, the next wonder is waiting to be found.